to the page where I'm just going to show you why something I had you memorize. When I told you this one last year and again this year when we reviewed it, I just did the 1 over analysis, arctan, urine analysis plus C, and I just told you what it was, and I said you're just going to have to memorize it, because in order to prove it, you need integration using Trig Sub, and that whole process takes a while to teach. So I'm going to just start by showing you why these are what they are. And then tomorrow we're going to use the process more, and actually this extends kind of for the whole week, and then we do a big group one that you're going to write out for AB on big sheets of paper, because they're going to do this as well. They're just not going to do the hard ones you guys are going to do. So you're going to do some hard ones, write them up, and I'm going to see that's where it goes in Calc 2. They're going to be able to do this. Anyway, you'll notice over here when we start doing some examples, all the integrands have roots, and they have like things that are squared under them, right? Like 2 squared and x squared. They look what I say like Pythagorean-y. Like this right here is a root, and it's got some squared things under it. Does that make sense? And that's what often will trigger integration by Trig Sub. If you're moving on into Calc 3, which some of you are, and should, it'll be assumed you were taught this. So that's another reason. If you're not moving on into Calc 3, just do it just because you know that you're not having a test on it. So just be good about it. All right, so let's write this model down that I told you to memorize. 1 over A, arctan, and then whatever that function is being squared over A. It's going to be important when we're doing this to understand that A's are constants, U's are functions of X. All right, so just keep that in mind. And then this was, again, plus C. That was that guy, and I just told you to memorize it and use it. Over here, this was no 1 over A. You're going to see why there isn't one. And it was arc sine. Sorry, I have a little cough. Not too bad. Arc sine, and it was just U over A plus C. So I'm going to spend some time showing you where these come from. But in order to do that, we need to go back to pre-calc for just a second. Are you ready? So in pre-calc, you learned, write it up here, that sine squared of an angle, and we're going to be using these identities quite a bit. They're called the Pythagorean trig identities. That's the one everybody knows. Do you know why that's true? Were you ever told why, or just that it was?
Just that it was.
Just that it was. So a quick thing to show you why it is what it is over here. You don't need to write it down. When we have a unit circle, what's its radius? What's the radius? 1 everywhere. Yep, that's why they call it the unit circle. So when I go out here, I will have gone 1 unit, correct? Or the radius is equal to 1. So I'm going to put a little r right there, but it's actually a 1. And this is x, and this is y, correct? The standard form of an equation that's centered, a circle centered at the origin with a radius of r is x squared plus y squared equals r squared. But for the unit circle, that's 1, correct? And the x is cosine theta. And if you're not sure why, it's because it's adjacent over hypotenuse. So cosine of theta would equal x over 1. That's why they always tell you cosine's the x. Does that make sense? And that goes in here, and you get cosine squared theta plus, and then y is opposite over hypotenuse, so the sine of theta is y over 1, and that would substitute in. So that's kind of why that is what it is. Does that make sense? You're going to need to use the other 2 that come from this, which is that sine squared is 1 minus cosine squared, and cosine squared is 1 minus sine squared. You get a 3 for the next one that you probably didn't memorize, but somebody told me it popped up on your BC test. It popped up under a root. Who told me that? With arc length. Like you ended up with a 1 plus tangent squared or something like that. Yeah. Right? Well, watch what that is. If I divide everything through by sine squared, I get a 1. Actually, by cosine squared. I get a tangent squared. Cosine squared divided by cosine squared is 1. And what's 1 divided by cosine squared? Secant squared. So it comes from dividing everything up here through by cosine squared. And you get this guy. You're going to be using that because you're going to be under roots. Right? Now, the other one that we're going to use is if I divided everything through by sine squared. Then I'd have 1. What's cosine over sine? Cotangent, right? I don't even memorize them. I kind of have to think it through. And what's 1 divided by sine squared? Cosecant squared. So those are the 3 Pythagorean trig identities, correct? And you need to know the other ones. So you might see 1 minus cosecant squared and be like, oh, I can replace that with cotangent squared. You're going to need to be able to manipulate them. But the reason I put those up there is because they come into play over here. So this is what I'm going to do. I'm going to start you off with why this is what it is. I'm going to let that function u, just in general, I'm going to pass off to trig. You know how when we do u sub, we pass off to u, right? I'm going to do passing off to trig with this. I'm going to let u be a tangent theta. So whatever that a is, if it was a 9, I'm letting it be 3 tangent theta. If this a was a 4, I'm letting it be 2 tangent theta. Okay, you can do that, math. You can let variables be anything you want as long as you don't break any rules. And as long as when I'm done, I go back to what I need. All right, so here we go. When I do a rewrite on that, so I'm going to do that rewrite down below because I'm going to be putting some more work in there. So leave some space. So right now I'm sitting there with, on the bottom, I have a squared plus u squared. So when I square that, I get a squared tangent squared theta. Does that make sense? I just replaced the u up above. All right, so I'm going to go back up here. On the top was a 1. So I'm just taking this, and right now I made a decision to let u equal a tangent theta. You'll see why I made that decision, and you'll be good at it in a couple days. So what are you going to let it be? Then my problem is I need to replace du. So what's the derivative of a constant times tangent theta? What would it be? It'd actually be du d theta, but what would the derivative be? Secant squared, right? And the constant would stay put. So my du can get replaced with a secant squared theta, and then we actually multiply that over. So when I go back to my original, the 1 stayed put, the a squared stayed put. I chose to let u equal this. Does that make sense? And then my du is going to be a secant squared theta d theta. Then I am going to factor on the bottom that a out, actually the a squared. And so I have an a squared. When I factor it out, I get 1 plus tangent squared theta. And then I have, over here, I told you it gets messy, secant squared theta d theta. Any questions so far? We're only going to prove these 2, and then we're going to finish our movie. So hang in there. Any questions on what I did? I factored, correct? What do you think I'm going to replace this 1 plus tangent squared with? Secant squared. So I'm going to go, and that's the whole point of these, is normally on most of them you're going to be trapped under a root, and to get out you're going to want to replace things. But this is actually going to be a squared secant squared theta. And then on the top I have what had to be my du based on my u choice. Now watch what happens with the canceling, and you'll see why you had to memorize 1 over analysis, arctan and analysis, is because somebody said that always happens when it's in that form. Notice the a's are going to cancel as well. So I end up with a 1 over a and then just d theta. Correct? And keep in mind 1 over a is a constant. So that's actually 1 over a, and then there's just basically a 1 in here. What's the antiderivative of 1? You might say x. I'd say yes if we were using that as a variable. This is theta. So this is 1 over a theta plus c. Now I have to go back and undo this. This problem wasn't about theta or secant squareds or tangent squareds. It was about a's and u's, correct? Now, so here's the last little thing when I go up here. If I let, right here, right? If I let u be tangent of theta, then I would say, well, then u divided by a has to equal tangent theta. And again, I'm trying to undo my theta. How do you undo tan? because I want to know what theta is. I've got to go back. I did a bunch of replacements to use some tricks. So I used to always say passing the buck to you. You're passing the buck to theta on this one. So I need to get untheta, right? So I will arctan my u over a to get what my theta is. All right? That's where that comes from. So I'm going to go down to the bottom, and I'll replace that. And that's why I told you guys, you just need to memorize that it's 1 over analysis, arctan urine analysis, because this is too much to explain. And because I just told you, when we're done at the end of the week, you're going to kind of know what to let the u be. I told you I'm letting it be this. My choice, though, was deliberate. So watch the next one. All right? It's going to be similar. You guys good? Just hang in there with
work it out.
It's cool stuff. All right. So on my next one, I'm going to do the same thing. It's called trig substitution because you pass off to the trig so you can use those identities, clean things up, and then you send it right on back to the original problem. So I'm running on a low battery. I have to plug that in. Sorry, I have one. I just don't have. So what I want you guys to do is write down, let u equal. So we're going to take our function u. You guys are being a little bit disrespectful, but I'll take it for today. Anyway, so on this one, I would write that we're going to do some substitution. It's called trig substitution. So I'm going to pass this guy off to a trig function. Keep in mind what I'm going to want to do. I'm going to want to get out from under the root, correct? I'm going to want to probably factor an a squared out. So what I'm going to let it be is an a, so I can do an a squared. You'll know why I choose this later. Not today. We're just going to do a little bit today. I'm going to start a rewrite down here. So leave some workspace in here. Right now I'm sitting there with 1 over the square root of a squared minus a squared sine squared theta. That's all I've taken care of, is getting that u there. What's my next thing do you think I'm going to do if you follow what I did on the other one? The du. Yeah, I have to pass, again, I always used to say pass the buck from x to u. Now we're passing it from u to theta. So I'm going to take my derivative of u, and it becomes a cosine theta. You kind of see where all these variables are kind of important. So when you guys used to leave off your dx's, I'd go, oh, that makes me so crabby. It really matters. So right now I'm going to go replace this guy with a cosine theta d theta. Boom. Any questions on that so far? What do you think? Are you good? You might only be saying, why did you choose that u choice? So what do you think I'll do on the bottom, just because you saw me do it before? I'm going to factor out the a squared, and I'm going to have the square root of a squared times 1 minus sine squared. They're very kind of similar. All of them have different trig twists, so I'm going to let you write that down because I wrote that super fast. All right, so an a is going to pop out from under the root, but what's 1 minus sine squared? Cosine squared, which is, that's why I had that choice. I've done enough of them where I'm like, okay, this is one where. So this is a squared cosine squared theta by using that trig identity. And then take a look at what cancels. If I asked you what cancels, what would you say basically? Everything, right? The entire integral cancels down. That's the beauty of the trig sub, is I'm actually just doing the antiderivative now of 1. Look at what I was originally doing the antiderivative of, and now I'm just doing it of 1. But what is the antiderivative of 1? Theta plus c. But now I have to take theta and send it back to a's and u's. So I'm going to go back up to the top, and I'm going to go see what I defined it as, right? And there it is. So this means that u over a is sine of theta. Must be. Correct? So what's theta? Arcsine urine analysis. That was a whole lot, in which that's why it doesn't need high levels of math really. It needs lots of trig, and I haven't told you why I made those choices yet. But do you see how the math works out? So it's kind of nice. And in AB, I had to tell them the same thing. I just said, you're just going to have to memorize it, and we'll deal with it later. This is the proof of it. So I'm going to go to the next page. I'm going to go until we have 8 minutes left, I think, on that movie. So I'm going to go, like, just to this part. So your goal in this is going to be to get out, and we're not going to do any examples until tomorrow, but you're going to want to get out from under the root, or let's call it the radical. So all of them are going to have these roots in them, and you're going to want to get out from under the root by using substitution, and you're going to be substituting for u, whatever the function of x is, okay? By using substitution for u, that results in, draw an arrow, one of those three. Because if you can get 1 minus sine squared, it'll pass to cosine squared, you'll root it, and boom, you're out. If you can get 1 plus tangent squared, you can replace it, you'll root it, and you're out from under the root. Similarly, this one is just this guy with a tweak. So on here, I want you to go like this. This is a constant, this is a function, this is a constant, this is a function, this is a function, this is a constant. That's how you're going to decide which one to use. So we're just going to do one that's not even in an integram, just getting out from under the root using some trig. So when you look at this one, you've got a constant, and then you have minus a function. And they're squared, but let's go like this. All right? So which one deals with a constant minus a function? The sine one. Exactly. So I know I'm going to try to get this, some sort of 1 minus sine squared. So I'm going to go down here, all right? And I'm going to try to figure out what to let my u be. The 4 is great, but I'm going to want it to pop out from under the root, so I'm going to want to be able to factor it, right? So what do you think I'm going to let this be? So that when I square it, I can factor a 4 out. 2, correct? And then which one did you say I was trying to get? You guys said over here, 1 minus sine squared, correct? So I'm going to let it be 2 sine theta. And this isn't integration, this is just using trig to get out from under a root. All right, so if I rewrote that, I'd have 4 minus, and, oh, sorry, this would be x. I should let x equal 2 sine theta, sorry. I'd have 4 minus, and then when I square this, I get 4 sine squared theta. That's why I made that choice. So that when I root it, I'm really rooting this, and then I can get out from under the root. How would I get out from under the root? What would it become? Yeah, it's going to become 2 cosine theta. So technically, these are equal to each other. You might be saying, what? Watch. Okay, I'm going to go back over here. I'm going to show you. Draw a right triangle, because we're going to be drawing lots of what we call reference triangles. The theta in this problem is always the angle. If my x was 2 sine theta, wouldn't sine theta have been x over 2? Right? And isn't sine from geometry opposite over hypotenuse? So wouldn't that have been x, and this would have been 2, if sine of theta has to be x over 2, correct? What would this side have been? Well, it would have been the square root of 4 minus x squared. Right? A squared plus b squared has to equal c squared. So c squared minus b squared has to equal a squared. It makes sense, doesn't it? Yes. So watch when I do 2 cosine theta. Go right back up here. If I were to do 2 cosine theta and go back, I do 2 times, and what's cosine? Adjacent over what? Cosine's adjacent over hypotenuse. Do you see how those are equivalent? There's just a variable change. I'm just kind of working the trig and working it backwards. That's all we're going to do today. Tomorrow we're just going to integrate 4 of them, and then we won't do anything else, so we'll probably be done early. I'm going to add, it gets heartwarming at the end. If you haven't seen it,